on player load during agility tasks. As you probably know, agility has been defined as a rapidly changing velocity or direction in response to an external stimuli, such as respond against the ball or the opponent or even your partner. This action has been considered particularly important during decisive moments or crucial moments during the game, such as creating goal-scoring opportunities. On the other hand, agility tasks seems to be associated with injuries or with an increased risk of injury due to the high external load and mechanical stress placed on the body. It seems also that the risk of injury is even higher when these movements are performed under fatigue. For example, Borodkar and Korts have been shown that a 6 minutes fatigue-induced bout is sufficient to cause significant change in lower extremity mechanics, particularly the hip and knee joint, during landing and cutting unplanned tasks. And since fatigue and decision-making tasks are not independent one of another during the game, it could be crucial for us to understand a bit of the underpinning mechanisms of these variables to prevent injury and improve soccer performance. With the introduction of triaxial accelerometer into GPS units, we are now able to measure those activities in the field in 3 dimensions through an algorithm called player load. Player load is the most common accelerometer-derived variable adopted by a range of sports practitioners and research to measure or to estimate mechanical load. With this in mind, the aim of our study was to examine the differences in player load during unplanned maximal sprint shuttles, pre and after an acute bout of fatigue. In order to achieve that, we have selected 10 soccer players, and prior to test, they were fitted with 3 triaxial accelerometers located at the upper back, where they are used to use on a daily basis, and one at the right and left ankle, as you can see in the field on the left-hand side. The agility test protocol consisted of 6 maximal unplanned sprint shuttle, interspersed by 2 minutes rest, and players were required to respond to an audio signal while they were accelerating under 3 different experimental conditions, at 1 second, 1.5 seconds, and 2 seconds. This video is going to show you an example of one of our participants perform a 1.5 second condition, and as we are going to see, I hope this works, there is a countdown beep, and players are required to start at the last beep, and when they start accelerating, when they hear the second beep, which is the experimental beep, they decelerate, they execute a 180 degrees turn, and they accelerate back. I think I need sound here. Can you arrange a sound for me? No. So, anyway, no problem. I'll just repeat again. So there is a countdown at this moment, and he starts to accelerate at the last. When they hear the beep, they execute a 180 degrees turn and came back. You can also see that we use opto jumps and timing gates to measure the distance covered and the sprinting time. Followed by 2 minutes, we then induce players under fatigue. So the fatigue protocol was consisted of 25 meters sprint shuttle under planned conditions, so they know where they go and where they come back, interspersed by 20 seconds passive rest, and we stopped the test when participants achieved 5% decrement in their sprint performance. Followed by 2 minutes, we then repeat the agility test protocol. We have been using the repeated measures ANOVA to look at the difference in time points pre and post fatigue, a per sample T test to look at the difference between first and last sprint during the fatigue test, and effect size were calculated. During the fatigue test, participants completed 12 maximal repeated efforts, and sprinting time was significantly reduced by 8%, as you can see in the figure on the left-hand side, from the first to the last sprint. Equally, player load was significantly reduced from the first to the last sprint. As you can see in the figure on the right-hand side, amongst all accelerometer locations. For the accelerometer location, the upper back, a reduction of 20% was identified, while on the right and left ankle, a reduction of 21 and 17% respectively. Despite the similarities in player load reduction amongst accelerometer locations, you can see that the player load was more sensitive at the ankles, more sensitive to change at the ankles. Also, the great reduction observed in player load compared to sprint performance seems to be consistent with previous investigations showing greater kinetic and kinematic change compared with sprint performance during overground repeated sprint protocols. But despite the fact that we indeed induce players under fatigue with the significant reduction in performance and mechanical profile, we did not find any significant change in player load during unplanned sprint shuttles, pre and post fatigue, for any of the conditions that we tested, with also a small effect size were found. Equally, we did not find any difference, any significant difference for the time to complete the tasks, for the number of steps, and for the distance covered. We found significant differences also between accelerometer locations during the agility task. This figure displays an example of one participant perform 1 second condition, and as you can see in the figure, the player load derived from the ankles seems to be almost threefold higher compared to the player load derived from the upper back, with a difference coming up to the 200%. So in conclusion, a 5% decrement in sprint performance equated to a mean reduction in player load of 12.5%, and players were indeed reduced to fatigue. However, this threshold was not sufficient to modify or to change or to cause significant change in player load and agility performance on subsequent unplanned tasks. In addition, player load seems to be more sensitive to change during fatigue and at the ankles. However, whether this change have implication for injuries remains to be answered, remains to be investigated. In terms of practical application, accelerometer device could be considered a sensitive tool to measure and monitor player load during agility tasks as well as during fatigue or repeated sprints. And since a combination of fatigue and decision-making tasks are suggested by a range of researchers as the worst-case scenario during the game, and we have to prepare our players for that, it seems that the low threshold fatigue-induced activity relative to individual fatigue profile seems to benefit soccer players, giving no significant difference were observed on subsequent agility tasks. It could be important in the future to also look at this effect, the effect of this threshold on more complex tasks, such as 1v1 situation where players execute higher numbers of turns or different angles of turns, as well as more complex tasks such as the small-sided game, 4v4 or 7v7, that are more game-related activity. Thank you very much for your attention.
We have some questions, Matt?
Thanks for the presentation. I was just wondering, with the first and last sprint, when you saw the reduction in player load, I know you looked at it for the pre-post agility, but did you look at the number of steps during the actual fatiguing test? And were the number of steps in that first and last sprint different, which may have accounted for some of that reduction?
Sorry, I didn't understand well. You mean the number of steps during the fatigue test?
Yes.
No, it was not counted.
Okay.
Because it's too fast. It's 20 seconds recovery. Yeah. So we were counting for the sprinting time and the distance covered.
Yeah, because could be, you know, when they're going to sprint, and it's a number of steps during the acceleration.
Yeah, it was not counted, but it would be possibly a good investigation.
Question at the back?
Did you evaluate reliability of the eligibility test?
No, we haven't evaluated the reliability because these are professional soccer players, so they have their duties in the club, and we have the opportunity to be with them just once. But if you consider these players execute this type of task on a daily basis, they are used to, but we haven't run reliability.
Stephen?
I really like the planned versus unplanned angle here, where you had an unplanned movement.
Yes.
Did you, or is your perception that the mechanics of the change of direction process changes in the unplanned versus planned condition?
That's a fantastic question, because I didn't bring this data here, but we have also compared the unplanned with the planned, and we haven't found any differences in player load, apart of 1 second condition that we had a large effect size, but we had no significant differences. So, and if we consider that 72% of the decelerations in soccer occur in less than 1 second, probably in 1 second we are going to find a high biomechanical change.
Andreas Fenhout from UCT. You didn't provide a model or concept in which you now discuss the data. So would you think it's more like a top-down fatigue, if you want to call it, neuromuscular fatigue that comes really more from the mental side, or is it more like a peripheral model that you use or interpretate your data in?
Well, it's a tough question because, as my colleague said before, it's a multifactorial. There is evidence showing that fatigue is more task-dependent. The mechanism of fatigue is task-dependent, and during repeated sprint, it seems that peripheral mechanisms play a bigger role, but also there are evidence that showing neuromuscular as the most contributing factor. So it's kind of controversial, and it's difficult to answer that. We need more investigation.
Hi, nice presentation. After the sprints, and they did the 180-degree turn,
Yeah,
did they always consistently turn on the same leg, same direction?
yes,
And then was dominant leg taken into consideration?
yes. So it was dominant leg. The dominant leg was chosen by the leg that they kick, and they keep consistent during all the turns, during the agility and during the fatigue test. But we haven't found any difference between limbs. As you could see in the player load of the two legs in one second condition, it was very similar. The level of the player load was very similar between right and left. But this could be interesting to look at asymmetries and try to individualize the data according to unilateral analysis.
Can I just ask the oxygen system which you used? What did you use the oxygen system for in the protocol?
So we have measured the distance they covered without the jump. We also tried to look at the contact time, but the data was not able to read, so it was very difficult. A lot of noise. We could not bring this data up.
Okay, thank you, Joao. Thanks a lot.